Today in lattice vibration, we are going to see the concept of quantization of lattice vibration. Actually, this quantization of lattice vibration is a very important concept because the several important problems related to the crystal lattice is discussed in terms of the quantization of lattice vibration. For example, the problem of a specific heat capacity of solids, in which we will discuss the classical theory, the Einstein theory and the device theory. All these theories are discussed in terms of phonons, and phonons, these are actually the quanta of lattice vibration or elastic wave. So this is a very important concept. Okay. So in this first lecture on this quantization of lattice vibration, we are going to know only some important facts regarding the phonons. And these phonons are actually what? These are just the quantum. These are actually the quanta or particle of acoustic wave, or you can say the lattice vibration or elastic wave. Okay. So what are the important properties and how we can detect these phonons in experiment, or what are the proof for the existence of these phonons, we will learn in this short lecture. And after knowing the important properties of these phonons, then we will discuss the physics of phonons after this lecture in the forthcoming lectures. Okay? I think you are definitely acquainted of the idea of electromagnetic wave and the quantum theory of radiation, because you have studied already quantum theory of radiation, and you can see videos on this quantum theory of radiation in my playlist of my channel. And you know that the energy of electromagnetic wave or electromagnetic radiation is quantized, and actually the energy quanta of electromagnetic radiation is known as photon. You know or not? Photons are actually the energy quanta of electromagnetic radiation or electromagnetic wave. Okay? Actually, on the same line, you can think that there will be some energy quanta, there will be the quantum of energy of acoustic wave, or you can say the elastic wave or the lattice vibration. Actually, the energy of lattice vibration or the elastic wave is also quantized like the energy of electromagnetic wave. As energy of electromagnetic wave, is quantized because it is defined in terms of energy of photons, and energy of photons are actually quantized. These have actually, when you say quantized, that means it has only discrete values. Actually, similarly, the energy of elastic wave or the lattice vibration is also quantized. This energy will also have discrete values only. Okay. So definitely, like the electromagnetic wave, this elastic wave will also have a quantum of energy. As you know, the quantum of energy of electromagnetic wave or electromagnetic radiation is called photon. On the same line, we say that the quantum of lattice vibration or the quantum of elastic wave or acoustic wave is called phonon. So what are phonons? Can you say no? Actually, phonons are the quantum or the particle of lattice vibration or the elastic wave. Just like photons are the quantum of electromagnetic wave or electromagnetic radiation. Similarly, phonons are the particle or phonons are the quantum of lattice vibration or elastic wave. Okay? And as you say that electromagnetic radiation is composed of, it is made up of photons. On the same line, you can say that the elastic waves in crystals are made up of phonons. Okay? When you say elastic wave is traveling, that means a stream of phonons are traveling. This is actually the quantum behavior of elastic wave. Okay? In fact, all types of lattice vibration in crystals comprise phonons. For example, if you are talking about thermal vibrations in crystals, okay? So this thermal vibration in crystals are caused by thermally excited phonons. And this is just analogous to the thermally excited photons of black body electromagnetic radiation. You know, when you increase the temperature of a black body, radiation is emitted. And that emitted radiation is actually the stream of thermally excited photons. In the similar manner, when lattice vibration is caused by the thermal excitation, by increasing the temperature, then actually in that very condition, the phonons which are responsible for the quantized energy of this vibration, that is called actually thermal phonons. That is thermal phonons. Okay? And similarly, you can also say that if you talk about the sound waves, then in case of sound waves, there are acoustical phonons. Okay? And excitations of the optical branch generate optical phonons. In the similar manner, when we will discuss in our forthcoming lecture the magnetic properties, then you will see that quantized unit of magnetic spin wave, quantized unit of magnetic spin wave is called Magnon. Okay? And the collective excitation of electron gas are called Plasmon. Okay? So these are actually the different quanta, different particles related to the different type of excitations or different type of waves or vibrations. Okay? Actually, all these particles, when you talk about photon or you talk about phonon, magnon, plasmon, actually all these elementary excitations are called quasi-particles. These are called quasi-particles. Okay? So in brief, I am just repeating. Whenever you will be asked what are phonons, what you will say? You have to say that phonons are the quanta means particles, quanta of elastic wave. Just like photons are the quanta of electromagnetic wave, in the same line you can say that phonons are the quanta of elastic waves. Okay? Now we will learn about some of the important property, particularly the energy of what will be the energy of a phonon. Actually, the energy of a phonon is measured in the similar manner as you measure the energy of a photon. Actually, the same formula evaluates the energy of both phonon and photon. Okay? So you can say that most of the concepts which apply to photons are also valid for phonons. Okay? For example, you know, photons have dual character. It means electromagnetic radiation has dual nature. It behaves like a wave and it also behaves like particles. That is called quantum nature of radiation. Okay, and there are several experimental evidence for the wave nature of electromagnetic radiation and its particle behavior or corpuscular nature. For example, electromagnetic radiation suffers interference, diffraction and polarization. And all these three phenomena confirm the wave behavior of electromagnetic radiation. Okay? On the other hand, the phenomena like photoelectric effect, Compton effect, these phenomena actually prove the quantum nature or the particle nature of electromagnetic radiation. Okay? So electromagnetic radiation has dual character. It behaves like a wave as well as particles. Actually, in the similar manner, our elastic waves also has dual character. They behave like waves as well as particles, and the particles of elastic waves are phonons. So you can say that phonons, which are actually the quanta of elastic wave or the lattice vibration, they also possess dual character. That is, they behave like a wave as well as particles, just like photons. So I have mentioned here that the concept of wave-particle duality holds good for phonons just like photons. Okay? So you can draw the properties of phonons just by knowing the property of photons. Okay? Now, the most important property of a phonon is its energy. Because we are talking about the quantization of energy here. So in this short lecture, I am just focusing about the energy of phonon. What is the formula for measuring the energy of photon? Definitely you have an idea. Energy of a photon of a radiation is given by E epsilon equal to h nu. Epsilon equal to h nu. Here, h is Planck's constant and nu is frequency. And in terms of the reduced Planck's constant, this h bar या h cross or h cut, this is defined as h divided by 2 pi. And this h bar or h cut is known as reduced Planck's constant. So h is equal to 2 pi h bar. Okay? So instead of h, I have written here 2 pi h bar. Okay? And this can be written as h bar times 2 pi nu. But can you say what is this 2 pi nu? Nu is the frequency, and this 2 pi nu is equal to omega, which is called angular frequency or cyclic frequency or circular frequency of the radiation. Okay? So the expression for energy of a photon is either written as h nu or h bar omega. Okay? This is the expression for energy of a photon. Actually, this result holds exactly in this form for the energy of phonon. So if you are now talking about the energy of a phonon, what will be the expression? Expression will be just this. That is epsilon equal to h nu or h bar omega. This also represents energy of a phonon. But in that case, this nu will be the frequency of the elastic wave, not of the electromagnetic wave. Remember it. In this expression, when you talk about photon, nu is the frequency of electromagnetic wave or electromagnetic radiation. But when you talk about epsilon equal to h nu or h bar omega for a phonon, then what is this nu and omega? Actually, in this case, nu is the frequency of elastic wave or it is the frequency of lattice vibration. Okay? But formula is same. Okay? I have mentioned it here. You can see that this h bar is equal to h over 2 pi, which is called reduced Planck's constant. Nu is the frequency of elastic wave, and omega, which is equal to 2 pi nu, this is cyclic or angular frequency of the elastic wave. Okay. So this is the expression for energy of a phonon, and that is just same as that of an expression for energy for a photon. Okay. Now let us consider a lattice is vibrating, and you know the vibration of lattice takes place in different modes, and if you want to define the energy of a particular mode of vibration in case of elastic wave with frequency nu or omega, then what is the energy of each mode of vibration in elastic wave? Actually, this result I have written here, epsilon n equal to n plus half times h nu. Or if you write h bar omega instead of h nu, you can write epsilon n equal to n plus half h bar omega. Actually, according to the modern quantum mechanics, that is the Schrodinger's quantum mechanics, when you deal with the problem of linear harmonic oscillator, then you find that the vibrational or oscillatory energy of the oscillator is given by this formula, epsilon n equal to n plus half h nu or h bar omega. Okay. So this same formula is applicable for the lattice vibration too. Okay. And in this case, this n is actually the non-negative integers, non-negative integer or positive numbers you can say, but n may be 0, n is 0, 1, 2, 3, but it is never negative, remember. Okay. And so you can see as the value of this energy of each mode of vibration of in an elastic wave is governed by this integer rule. So definitely this energy epsilon n will have only discrete values, not continuous values. It means the energy of different modes of vibration in elastic wave is not continuous, but the energy spectrum will be discrete, and you can find all the possible values of this vibration of elastic wave. Okay, vibration of this lattice using putting the different values of n. So let us see here. Actually n represents the number of phonons in the mode. Okay, h bar omega, you know, this is the quantum of elastic energy, or you can also say unit of elastic energy, and this is actually equal to energy of a phonon, as you have seen earlier. Now you can see that when epsilon n is equal to n plus half h bar omega, then if I ask you what will be the minimum value of this epsilon n, its minimum value can be found by taking the least value of this n, and you know the least value of n is 0. So when n is 0, then epsilon n, which is denoted by the symbol epsilon 0, that will be what? That will be simply equal to half h bar omega. So this is actually the minimum energy of the vibrating lattice. The energy of the vibrating lattice can never be less than this, or that cannot be 0. According to old quantum theory, this value was taken 0, because in old theory epsilon n is given by this formula, n into h bar omega. So according to this formula, when n will be 0, then epsilon naught will be equal to 0. But according to modern quantum mechanics, epsilon n is equal to this much, n plus half h bar omega. So, according to this formula, the least value of energy of vibration will be equal to half h bar omega. And actually, this least value of energy is known as 0 point energy of the mode. This is called 0 point energy. Why it is called 0 point energy? Actually, the reason behind this is what? The reason is, if you keep the lattice even at 0 Kelvin temperature, according to classical theory, at 0 Kelvin temperature, the lattice vibration will be completely stopped. And so, the vibrational energy should be 0 at the 0 Kelvin temperature. But this is our classical idea. According to quantum theory or modern quantum mechanics, even at 0 Kelvin temperature, the lattice vibration is not completely stopped. Even at 0 Kelvin temperature, our oscillator has this much energy. This is half h bar omega. So you can also say that this is the energy of the lattice vibration at 0 Kelvin temperature, at absolute 0 temperature. And that's why this energy is called 0 point energy. Okay? So why it is called 0 point energy? I think you have now a clear cut idea. Okay? Yes or no? Definitely you have to say yes. Okay? Now, substituting the different values of n, you can find the corresponding value of this energy. Let us say, when you take n equal to 0, you can see, when n is 0, then epsilon will be equal to epsilon 0, and that is half h bar omega. So in this figure, I have indicated by this line this energy half h bar omega, which represents actually the least energy or the 0 point energy. The another value of energy will be found by taking the second value of n, which is n equal to 1. You cannot take any number between 0 and 1. After 0, you have to take 1. Okay? And so, the corresponding energy will be what? This will be 1 plus 1 by 2 times h bar omega, n plus half, but n is 1. So this is 3 by 2 h bar omega. Okay? And when you will take n equal to 2, the energy will be 5 by 2 h bar omega, and so on. Okay? So you can see that the energy of lattice vibration is not continuous. It has discrete values. So the energy spectrum is discrete, not continuous. You can see. After half h bar omega, the lattice vibration will have only the energy 3 by 2 h bar omega. All the values of energy between half h bar omega and 3 by 2 h bar omega are prohibited. That cannot be, that those are not allowed energy. Okay? So you can say that the energy spectrum of this lattice vibration will be discrete. And I have shown here in this figure. But here there is a very remarkable fact. Actually, the quantization of lattice vibrational energy has an important consequence. You can see, when you take the difference of energy between the two successive energy levels, what will be that difference? You can see, when you find epsilon 1 minus epsilon 0, you can see this will be 3 by 2 minus half times h bar omega. Okay? And this will be h bar omega. Okay? Similarly, if you find epsilon 2 minus epsilon 1, what will be this? You can see this will be 5 by 2 minus 3 over 2 times h bar omega. and that will be again h bar omega. So you can say that actually the energy levels during the vibration of lattice are equally spaced, and the energy separation between the two successive energy levels is constant, and that equal to h bar omega. That is equal to h bar omega. Okay? And actually, if we are talking about the first order approximation, then the energy changes takes place between the two closest energy levels, or the adjacent allowed values in this case will be equal to delta epsilon equal to plus minus h bar omega. Here this minus sign represents what? If you take let us say epsilon naught minus epsilon 1, then this will be minus h bar omega. If you take epsilon 1 minus epsilon 2, then this will be minus h bar omega. Okay? So actually in practice it is found that the transition of the phonon takes place only between the adjacent energy levels. Okay? It is not possible that a phonon will jump from first level to the fourth level, or fourth level to the first level, but first to second, second to first. Okay? So in this case, actually the change in the number of phonon is also equal to plus minus 1. Actually this minus sign again I am saying you, this represents that the transition of phonon from the lower level to higher level. So you can say in general the energy change corresponds to a gain or loss of a single phonon. Plus sign actually represents the loss of a phonon, and minus sign actually represents the gain of a phonon. When a phonon will be gained by the lattice, then the state from n barabar 0 will become n equal to 1. But when the phonon in this state n equal to 1 will be released, then our system will be in this state n equal to 0. So actually in this condition there is a loss of phonon or a gain of photon whose number is equal to 1. Okay? So I think you have now an idea of energy of a phonon and what is the energy of the vibration of lattice in a particular mode. Okay. Now we will see another important fact regarding this phonon, and this is actually the temperature dependence of the number of phonons. Actually, when you talk about phonons, you know these phonons are the quanta of elastic waves or the quanta of lattice vibration. But how many phonons will take place, will be involved in that vibration? That depends on temperature. In fact, the number of phonons in a particular mode of vibration at temperature T is given by this formula. This n inside the angular bracket represents the average number of phonons in a vibrational mode, and that is given by 1 over e to the power h bar omega over kb into T minus 1. Actually, this formula is obtained from Bose-Einstein statistics, because I will explain sometimes later that these phonons are actually bosons and obey the Bose-Einstein statistics. Okay? So remember this formula. At temperature T, if you have to find the average number of phonons in a particular vibrational mode, that is given by this n equal to 1 over exponential h bar omega over kb into t minus 1. Actually here, this kb is a universal constant, and you have definitely an idea of it. This is called Boltzmann constant. Okay? And T is the absolute temperature of the crystal. So you can see, if you think that T is increasing, if T increases, then what will happen to the value of this N average? When T will increase, h bar omega by kbt, this will decrease. And if the power on exponential will decrease, then e to the power h bar omega by kbt, this will decrease. Okay? But this exponential factor is in denominator. So when denominator will decrease, the final result will increase. So finally you can say that when temperature increases, then this average number of phonons in a particular mode of vibration also increases. Okay? And in the similar manner you can also say that with decrease in temperature, this number n of phonon decreases. So remember, if the lattice vibration is taking place at a particular temperature, there will be a certain number of phonons taking part in a particular mode of vibration. When you will increase the temperature, the number of phonon will get increased. But if you will decrease the temperature, then the number of phonons will get decreased. Okay? Now let us consider an extreme condition. We consider that we are decreasing the temperature, and finally we make the temperature tending towards 0 Kelvin. If the temperature is tending towards 0 Kelvin, then what will happen? You know, this exponential factor e to the power h bar omega divided by kb times t. What will be this? Since t is 0, so h bar omega divided by kb into 0, and that will be h bar omega divided by 0, and that will be undefined, infinity. So you can say when t tends to 0 Kelvin, then this exponential factor also tends toward towards infinity. But if this exponential factor tends towards infinity, what will be the value of this average number n? What will be this? You can see now this exponential factor is infinity. So n average will be given by 1 over infinity minus 1. But infinity minus 1 is simply infinity, and so this is 1 over infinity. And you know 1 over infinity is 0, because whenever you will divide a finite number by infinite, the result is 0. So what you are seeing here, you can now say that when t tends to 0 Kelvin, then this average number of phonon taking part in a particular mode of vibration also tends to 0. And it means when temperature will tend to 0, then number of phonons in a particular mode of vibration will be also 0. And that's why, according to classical theory, at absolute 0 temperature, the energy of vibration becomes 0. Okay? So this is the effect of temperature on the number of phonons in a particular mode of vibration. Now we will talk about the statistics. It means, there are three statistics. First one is called Maxwell-Boltzmann statistics, which is also called classical statistics. And there are two quantum statistics. And what are those two quantum statistics? Those are Bose-Einstein statistics and Fermi-Dirac statistics. Okay? Actually, this phonon is a quantum particle. These are indistinguishable, not distinguishable. Classical particles are distinguishable. Okay? So, this particle must obey the quantum statistics. But which quantum statistics? Actually, it is seen that these phonons have integral spin and symmetric wave function, just like photon. Phonons have integral spin, that is, its spin may be h bar, 2h bar, 3h bar, and so on. These are the spins or spin angular momentum, you can say, of phonons. Or in units of h bar, you can also say that phonons have a spin 1, 2, 3, and so on. And if phonons have integral spin, definitely this will not obey the Pauli's exclusion principle, and its wave function will be symmetric. Okay? And you know, a particle which has symmetric wave function, which has integral spin, which does not obey the Pauli's exclusion principle, such a particle is called boson. And boson, why it is called boson? Because it obeys Bose-Einstein distribution law. So, finally you can say, since phonons are bosons because these have integral spin, symmetric wave function, they do not obey Pauli's exclusion principle, so these are bosons, and so the statistics obeyed by phonons is Bose-Einstein statistics. So whenever we will talk about the energy distribution of phonons, we will think about Bose-Einstein distribution law. In terms of Bose-Einstein statistics, you can make the calculation. Okay? Now, since bosons have particle nature, okay, and so these bosons may interact with other particles like another phonon, or interaction of phonon may take place with another phonon, with a photon, with an electron, with a neutron, and so on. And this interaction of phonon with other particles is known as scattering. Actually, in our third video on this phonon, we will see the scattering problem too. Here I have only mentioned this scattering as a property of phonon, but the complete problem on the scattering of phonon by photon we will discuss in our third lecture in very detail. Okay? So you can say that a phonon may suffer a scattering when it is interacted by another phonon or electron or neutron and so on. Okay? So these were some important properties related to, of the phonons. Okay? And I think you have definitely now a clear-cut idea of phonon, what are phonon, what are its important properties. Okay? But now we are going to see the experimental evidence for the existence of phonon. Can you say that experiments support the existence of phonon or not? Actually, you know that photon, which are actually the quantum of electromagnetic radiation, actually the energy of electromagnetic radiation is quantized, and that is discussed in terms of photon. So actually there is a direct experimental evidence, direct experimental proof of the quantization of energy of electromagnetic wave. You have definitely studied photoelectric effect and Compton effect, definitely studied. You know, photoelectric effect was previously tried by different scientists for its explanation on the basis of the wave theory of radiation. But on the wave nature of radiation or electromagnetic wave, photoelectric effect cannot be explained. Einstein explained photoelectric effect taking the quantum behavior of radiation. So, when we consider that radiation is made up of photon and photons have energy h nu or h bar omega and momentum h by lambda, and we also consider that energy of electromagnetic radiation is quantized, then photoelectric effect is explained. So explanation of photoelectric effect, and this photoelectric effect has been also verified experimentally. So the phenomenon of photoelectric effect is an experimental proof of the existence of photon. It is a direct experimental proof of existence of photon, not phonon, photon. But here we are talking about for the experimental evidence of phonons. Are there direct experimental evidence for the existence of phonons? Answer is no. There is no direct experimental evidence for the quantization of energy of an elastic wave or lattice energy or phonon. There is no experiment. But in direct way, we see that phonons exist. So there is no direct experimental evidence, but indirectly we can see the proof of the existence of phonon. So I have mentioned it here. You can see the following experimental facts forcefully suggest the existence of phonons. And what is the first experimental fact? Actually, in this lattice vibration, we discuss a very important problem of lattice heat capacity of solids. Okay? But I have already discussed the lattice heat capacity of solids in my previous videos in the playlist of thermodynamics, where you can find the Einstein's theory of lattice heat capacity, Devi's theory of lattice heat capacity. You can find. I have already provided this video earlier. Okay? Although this is the subject matter of lattice vibration, but I have provided this in the playlist of thermodynamics. Okay? And you can find it. When you will study either classical theory of lattice heat capacity or the quantum theory in which you study Einstein theory and Debye theory, actually all theories agree at one point. When temperature of the solid tends towards 0 Kelvin, then the lattice heat capacity of all solids tends to 0. This is an experimental fact. When temperature of the solids tends towards 0 or approaches to 0, its lattice heat capacity also approaches to 0. This is actually a very important experimental fact. But how we can explain it? If you will try to explain that CV tends to 0 when T will tend to 0, you must have to take under account the quantization of lattice energy. You must have to take. If you will not take the quantization of lattice energy, or if you do not think about the phonon, that lattice vibration is composed of phonon, then you cannot prove this. This can be proved only when we consider that lattice vibrations are quantized in terms of phonons. Only then this experimental fact can be proved. And so on this basis you can say phonons exist. Phonons exist. Okay. This is actually the one indirect experimental proof for or experimental evidence for the existence of phonons. Now we will see the another evidence. Actually, we have already studied the scattering of X-rays by a crystal, and also I have discussed in my previous video in the same playlist, Condensed Matter Physics, the scattering of neutron by a crystal. You have studied. And actually, whenever X-ray or neutron get scattered from a crystal, this is your crystal, let us see here, and I have shown here either an X-ray or a neutron strikes this crystal, then what will happen? Then actually it is found that the energy of the scattered X-ray or the scattered neutron is not same as that of the energy of incident X-ray or incident neutron. If you consider that E is the energy of the incident X-ray or incident neutron, and E prime is the energy of the scattered X-ray or the scattered neutron, then it is found that E prime is not equal to E. E prime is not equal to E, but it is seen that E prime is actually less than E. There is a loss of energy. Okay? It is an inelastic collision. Similarly, if P is the momentum of the incident X-ray or the neutron, and P prime is the momentum of the scattered X-ray or neutron, you can take this P as a vector because P is a vector quantity. Okay? Then it is also found that P prime is not equal to P. It means momentum of the X-ray or neutron also get changed after scattering. How much momentum will change? How much energy will change? What will be the change in energy or change in momentum? That can be found only considering that in this scattering process, if a phonon, either one phonon or more than one phonon is created, and that also recoils here. Okay. So here actually I have shown in this figure, this is the produced phonon in this scattering process, and its energy is h bar omega and momentum is h bar k, where k is wave vector. And you will see when we will discuss the problem of scattering in our third video on this lattice vibration, then you will see that actually this E will be equal to E prime plus h bar omega. This is energy conservation. Okay, this will be satisfied. Actually, here I have considered that there only one photon has been produced, but in this process it is possible that more than one phonon is produced. Okay, so this change of energy and momentum in this process corresponds to the creation of one or more phonons. The energy lost appears in the form of phonon. Okay? You can say here that this E minus E prime, see from here, E minus E prime is equal to what? This is h bar omega. So what is the lost energy? That will be equal to energy of a phonon. So If there is a loss of energy of X-ray or neutron during this scattering by crystal, then that lost energy appears in the form of phonon. So this scattering of X-ray or neutron by a crystal is an indirect evidence for the existence of phonon. Okay. In fact, by measuring the energy and momentum of the scattered X-rays and neutrons, we can determine properties of phonons. Several properties of phonons can be determined. Okay. So this is all about the phonons, an elementary idea of phonon. But our next lecture and after that one lecture more will be related to this phonon. Actually, in our forthcoming lecture, we will talk about the momentum of phonon. And after that, we will learn about the scattering of phonon by a photon. Okay? So there will be 2 more videos on this phonon physics. Okay? Thank you very much.